apologize for the math-like nature of this morning's first couple hours. That's what I'm going to claim is the reason for the. It's certainly not my exciting and dynamic voice. I think that would be a problem at all. Okay, but what we're going to start talking about now is actually, we've talked about signals themselves. That was what we talked about yesterday and for this morning, part of the morning. Now I want to talk about the transmission media itself. We talked about what we're going to send. Let's talk about the channel, what we're going to send it over. So we're going to talk about wired transmission, talk about a couple models, then we're going to talk about transmission lines. So first off, power transmission, we've got some generator that has a power P gen, and then a load, which is power P delivered, and then there's a long wire with impedance. So this, back to that Edison-Westinghouse debate we talked about. What they wanted to do is maximize the delivered power. And that's the general idea of whether it's power generation to run stuff with the electricity out of the wall, or whether it's a signal. We want to maximize the amount of power that we're sending. So a couple ways to do it. Number one, we can use AC, which means that wires and the loads tend to be inductive. When they're inductive, what happens? What's the impedance of an inductor? J omega L, right? So as the frequency goes up, your right. Well, impedance goes up for induction. Right. So that attenuates my voltage more, which means that attenuates the power, right? We lose power going through it. So we also lose power if the current's out of phase with the voltage. Now we can fix that by adding capacitance to get phi back to 0. But if they're out of phase, since power equals I times V, if they're not in phase, we're not going to get peak power delivered. So the other way is to use DC. Then we only have to worry about the resistance in the wires. So power is I squared R, so we either need to have R be really small, which means superconductors, and apparently there weren't many around during the Edison-Westinghouse debate, or we've got to have I be small, which is what Edison said. So Edison says that I needs to be small. So how do you make I small? Yeah, you have a high voltage but high resistance, and then your I is going to be small. Problem with that is then you have to use this really high voltage with the high resistance, and anytime you short something or touch it, yeah, you're going to get zapped almost always and killed. So then that means we need to transform down the voltage when it comes out in somebody's house, but wait, transformers only work with AC. So that's kind of what sunk Edison's DC idea, is that the DC voltage had to be really high and we couldn't transform it down. The only thing you could do was make a voltage divider and dissipate a bunch of it as heat. So it actually would have worked fine in the wintertime. Everyone would gather around the big resistors and keep warm, but not so well in the summer. Okay, so power transmission, the generated power equals the high voltage times the low current, and the delivered power is the generated power minus the I squared R and X, remember, was reactance in the wire. So in a neighborhood, we transform it down to 440. One phase gets dropped to the house. Both wires are hot. We already talked about this. Then our house wiring, the typical circuit is, here come the two hot wires from the street, and then in the center we have a ground wire. So we hook a fuse or a circuit breaker to one of the hot wires. It goes out to all the load in the house, comes back at the other end, attaches to the neutral or the ground, and that gives us 120 volts from here to here. Then the other half of the stuff in your house is on this other one, so half your house is out of phase with the other half, but it really doesn't matter, right? Okay. Then you do a bunch of these in a star architecture because every breaker has its own circuit like this, right? And then all your loads are just in parallel. So what happens when your kids start going around the house and plugging something into every outlet? You're dropping the impedance. Yeah. There we go. Anyway. Okay, so now what is GFI or GFCI? Mm-hmm. And what's that for? Don't we already have ground? Yeah, if you drop the toaster into the bathtub, don't you already... Number one, there's already a circuit breaker there.
Yeah, but it takes a while for it to break.
Okay. Yeah, it takes longer for that circuit breaker to break than it does to kill you because of the toaster in the bathtub. And so you know GFI was invented by man because it's usually the ladies that like to toss the toaster in the bathtub with their no-good husband. So men then had to come up with GFI. Now, the idea is, what is it that trips the circuit breaker or blows the fuse? Let's use a fuse because it's easier to think about. What is it that blows the fuse? Yeah, you get a lot of current flowing through it, so, and it has a filament with a resistance, right? More current flows through it, more power gets generated. That power is getting dissipated as heat, which melts the filament and breaks it. So it's just the total amount of current flowing eventually burns out the fuse. And breakers work pretty much the same way. The total amount, the magnitude of the current is what pops the breaker. GFI is a little bit different. What it does is looks at the slope of the current. So if the slope of the current suddenly changes, it recognizes we're going to get up to a lethal level of current here pretty soon. So as soon as that changes, it pops. So that means it can react a lot faster. Number one, because it's usually closer to the load, and number two, because it pops because of the slope of the current rather than the magnitude of the current. Does that make sense? Kind of. Does it matter?
Still not fast enough to say.
Maybe. I don't know. It's actually proved useful in a lot of situations. I mean, you still get a good zap, but it usually does a pretty decent job. Now, the other thing that's good for is making people really, really pissed off because somebody puts one in one of these parallel architectures and doesn't say that it's all connected together like that. So like half my basement is behind a GFI that I didn't know about.
Yeah, on-post housing decides to put the key circuit inside a locked the AC unit closet that we don't have access to, and that's what powers all the external outlets, so my wife can't run anything outside. And so we have to put a work order in for them to unlock the door just to push it. And it's
just to push the button. Yeah. Wow. Yeah. I spent a week one time with the lights off in the basement running an extension cord down to my computer because, I mean, I had tried everything. I had pulled the breaker. I'd replaced it with a different breaker. I had pulled that off and put it in a different position in the box. I mean, nothing was working. And it was, it would measure fine. I thought, I've blown a wire someplace in the wall. I'm going to have to tear out half the wiring in my house. And luckily, my son's looking around and he's like, why does this one have a button on it? I'm like, well, it's a GFI. That's for where there was supposed to be a bathroom here in this basement. Wait a minute. Why don't you try pushing that button? Oh, crap.
Well, the funny thing in housing, too, is none of the outlets in the upstairs master bathroom or the control circuit's like further somewhere else. It's not even in there, so.
Right.
If we got one in the garage that controls some of those outside outlets that you might look at.
Yeah.
It's odd places.
Yeah, so the moral of the story is if you've mysteriously got your power out in part of your house and the breaker's not popped, start looking around for GFIs in just random places. See, make sure they're all still set.
There's the new ones that are the arc fault.
Oh, yeah.
And they're even more sensitive.
Yep. Yeah, those are yeah, and it's good for safety, but I'd rather take a little voltage now and then to not have the hassle of All right. So a couple things. There's a bunch of different models we use. We used the electronics model earlier, which basically said that wires were just magic paths that connected the points together. There was no delay, there was no resistance, they were just ideal circuit connectors, right? So that's one way. When we start talking about a longer transmission line, we have to start thinking about the fact that the wire itself has resistance, right? So we talk about the resistivity, and we talked about this during electronics a little bit. So we think of it as a loop with some series resistors in there. That takes care of the resistivity of the wire. But then we also have to add reactance, because there's inductance from the wire itself, there's capacitance between the wire and ground and between the wire and the return wire. So that's one way to do it. We can create a model of a set of filters with using Fourier theory and do a bunch of really annoying stuff we won't do. Or we can just write the wave equation and Maxwell's equations. So I figure that's probably the best way to approach it. Is we'll just, you guys all know Maxwell's equations, right?
Maybe we see it.
All right, hold on.
There's a PDF of it under EE courses, and not buried under any folders. It's like the first thing on there, and it's got like a dumbed down layman's terms of explanation of each of them. There's 4.
So we won't be using that because we don't want dumbed down. We want this shined up and sparkly, man. No, that is actually cool. I'd like to see it.
I'll print it out.
Okay. So whoops. Where did that go? Okay, Maxwell's equations. Here they are. The integral over the surface of E dot product of dA is Q over epsilon naught. Gauss's law. Let's just go straight to Maxwell's regular equations. Okay, what is this thing? Anybody know? It's upside down delta. This is delta standing on its head, dot E equals rho over E naught equals 4 pi k rho. All right, this, you can go through all of this kind of stuff and figure this out. This is really, really, really annoying to do all of this. This is the right way to do it, but the main point is most of the time you're not going to care about that much of the detail. So what we'd rather do is have a slightly simplified model. Cool. All right. So other thing that we can do. Oh wait. Yes. All right. Yeah, this is actually really cool. Set of coupled equations relating magnetic and electric fields to one another and their sources, and then shows how the time-varying current generates a circulating and time-varying magnetic field. Okay, and so we basically do integrals around a closed path to deal with Maxwell's equations, right? How many of you are excited about the idea of integrals along a closed path? A couple of you. That's what it's, there's usually a couple. Now, in general, we're probably not going to reinvent the wheel every time and go all the way back to Maxwell's equations. So what we can do is use a transmission line model. Okay? A couple ways that this works. Number one, if we transmit a high frequency signal on a transmission line, we get hosed twice. Number one, stray capacitance between conductors. So let's look at what we've got when we're sending this thing. So here's our source. Actually, let me instead of drawing it as source, let me just draw it like a voltage source, okay? So we've got stray capacitance between the conductors. And out here someplace is my load. Okay, number one, now we've got capacitance in parallel with the load. And capacitance, the impedance of that is 1 over j omega c, right? Which means as omega gets bigger, that gets smaller, and since it's in parallel with the load, we start losing power to the load because it's going through the capacitor, right? Okay, next thing is natural wire inductance along the wire's length. So we have inductance here. This is j omega L. So we have inductance in series with the load. So if you think of that as being a voltage divider, the higher that impedance of the inductor gets, the less power there is to deliver to the load. So as we increase frequency, both the capacitor and the inductor screw us up. So yeah, the capacitor is a path so that some of the current doesn't reach the lines, and this acts with the wire resistance as a series impedance. So speaking of wire resistance, hey look, there's a space here for it. It's like I knew it was coming. This is just R, okay? So we have a wire resistance in there too. Now, all of these things also increase with length. Longer the wire, I mean, we already saw inductors, the longer the coil, the more turns on the coil, the greater the inductance. Same thing with just natural inductance. Longer the wire, more inductance. Same thing with capacitance. Longer the wire, more area of capacitor we have, so the greater the capacitance. So, higher frequency hoses us, longer length causes problems. Both of those. And also the resistance. As we expand this, you get more resistance. So, higher the frequency, the lower the reactance, lower the current reaches the line's end. Higher the frequency, higher the series impedance, and lower the current that reaches the line's end. So that hurts us both ways. Now, can we view a transmission line as a filter? Well, you saw the filters we did in basic electronics had an LR and a C in them, right? Oh, hey, look at that. Here's an L, R, and C all in a transmission line. So yes, okay, we can change that. We can either make a synthetic circuit elements or natural capacitance and wire inductance, amplifiers, coupling capacitors, all of this stuff make natural filters. So any copper wire is a natural low-pass filter. So if you run something through Cat5 cable, you are low-pass filtering it. High-frequency signals get attenuated more than low-frequency, and any kind of square waves or things have high-frequency components, so those high-frequency components get affected more than low-frequency components. And the problem is it's a little more complicated than a filter because it also changes the phase and messes with things like that. So what we're going to do is either wire pairs or coax. We can both model those as transmission lines. We can use them, if we use waveguides, we pretty much just use Maxwell's equations. How many of you have dealt with waveguides before? A couple of you. Does anybody know what a waveguide is?
It's a rectangular metal tube that can deal with the extremely high frequencies used by satellite.
Okay. Right. Yeah. Once you get up into microwave frequencies, you can use a waveguide, which is essentially a way to have. I mean, it's wireless because it's actually going through the empty space in the middle of the waveguide, but it's guided like a wired transmission. So it's kind of a hybrid of wired and wireless. It doesn't attenuate like wireless does. It attenuates like wired, but it transmits through the air in the middle of the waveguide. So it's kind of a weird thing. So you pretty much have to use Maxwell's equations. But for copper wire and coax, we're going to use transmission line model. So we can model the circuit as model the transmission line as a ladder circuit, which you notice here we've got the R and L in series and a C in parallel. What's this G in parallel? Goodness in parallel. Exactly. That's it. Oh, actually, this is badness. This is G. No, close. G weirdly is measured in mhos, MHOs. Everybody, what's that? It's called admittance. Yeah, and it's the opposite of resistance. Basically, what it is this is essentially whatever shorts across the gap there across the insulator. And then we just treat it as a resistor, though, basically. So we didn't put it in here because it's really small, but sometimes you'll see it in there.
So it's actually not there, it's just a representation of the...
It's just a representation of the amount that's leaking. In fact, all of these things are. R here is just the resistance of the wire itself. G is the permeability of the insulator. C is the capacitance between the two wires, like in your twisted pair. And L is the inductance, especially when you have a twisted pair. I mean, that's just a big, long, stretched out inductor, isn't it? Because it kind of coils around. So all of these things are just natural, inherent in the wire. Okay, so then we let delta x here, which is the length of one of these little ladder circuits, go to 0. We solve the differential equation for v of x of t and I of x and t, which is v at a particular position and time. And we get v equals VL e to the j omega t e to the gamma x plus VR e to the j omega t e to the minus gamma x, where VL is the leftward traveling wave, VR is the rightward traveling wave, and gamma here is alpha plus j beta, and it's a function of R, X, L, and XC. Doesn't this sound good? No. Alpha gives you the attenuation. J beta. Fair enough. I mean, that's okay. Remember how somebody was saying that a lot of times in schools they teach you an easy way and then start adding complexity because you've understood the first thing. Yeah, we're doing it exactly opposite of that. I'm going to show you the impossible way to do it first, and then you'll be happy when you see, oh, it's really not that hard when we do it. Okay, but you can just plug it into this equation. So Vx of t equals e to the alpha x times e to the j omega t plus beta x. Oh, you notice here e to the j omega t is just a sinusoid with a phase of beta x, right? Okay. And e to the alpha x is just an attenuation. This is just a logarithmic attenuation. So this is the equation for a traveling wave, and we've got omega equals 2 pi f, and beta equals 2 pi over lambda. So beta is just an inverse of the wavelength, but with the 2 pi taken out. Okay, so omega over beta equals f lambda. And f lambda gives you 1 over seconds times meters. So that's meters per second, which is a velocity. Make sense? That's the velocity of the traveling wave. Does the wave travel at the speed of light in a wire? No. What speed does it travel? About 1/3 to 1/2, 2/3 maybe, depending. Okay. So now here's the important part of all of this. The rightward wave is VR e to the minus alpha x e to the j omega t minus beta x, and we've got a similar one for the current. So we can solve that so that V over I equals Z naught, which is R plus j omega L over G plus j omega C, and then the square root of that whole thing. Characteristic impedance is a real number, and it's just the characteristic impedance for a wire. It doesn't depend on the wire's length. It's not like resistivity. It's just the impedance of that wire regardless of its length. Okay? So let's look at the limiting cases. If R and G are big, so at low frequencies, j omega L is going to be small and j omega C is going to be small, then Z naught equals square root of R over G, which is square root of R wire resistance times the interwire resistance. If R and G are small, so at high frequencies, Z naught equals the square root of L over C, right? Because then this part, the j omegas cancel out, and the R's and G's are small compared to j omega L and j omega C. So we get square root of L over C. So both of these, you notice, are real values. In general, we're concerned with mostly high frequencies. So our phase velocity is 1 over Z naught, which is 1 over, 1 over square root of LC, which you've seen before, right? What was 1 over square root of LC?
It was the omega naught, which is the resonant angular frequency.
Yep, exactly. Yeah, the resonant frequency, F naught. Wait, no, yeah, you're right. Omega naught was 1 over square root of LC.
Why with the under-limiting cases, I don't understand why the resistance and G small will give you a high frequency.
Okay. Well, all right. Let's look at this. Let's just plug in some numbers then. Let's say that R equals 100 ohms and G equals 100 ohms. Okay, and L equals 1 Henry. C equals 1 farad. I don't know. This doesn't really matter, but okay. So if omega is small, let's say omega is small, like at DC, omega will be 0, right? So we're going to say square root of 100 plus J, and omega is 0, times 1 Henry over G plus J times 0 times 1 farad. So these are very small at low frequencies, right? So all that's left is square root of R over G. Does that make sense? Well, because we plugged in 0, this is omega right here. So at DC, omega is 0, so all the j omega L and j omega C both become 0. That part okay? Now let's look at the other side. The other way is a little more complicated. So now we've got 100, let's say at 2 gigahertz. Right? So 100 plus J, now 2 gigahertz is 2 times 10 to the 9th, right? times 1 Henry, whoops, over 100 plus J 2 times 10 to the 9th times 1 farad. Now, 100 is basically negligible compared to 2 times 10 to the 9th, right? So basically we can just ignore that because it's really tiny compared to the other part, and we're left with, and then the J's cancel out, and the omegas cancel out, and we're left with the square root of L over C. Does that make a little more sense? All we're saying is once omega gets big,
What is that stuff for you?
inductance. So it's just the inductance over the capacitance. Yeah, we got to keep it complicated so that nobody finds out the Telecom secrets and realizes that they don't need to pay us to do it.
Yeah.
Okay, so what we're saying, and this makes sense if you just think about it in general terms. At DC, their inductance and capacitance have no effect because they're based on change in current, right? And at really high frequencies, almost all the effect comes from the inductance and capacitance because we're changing current all the time, so the resistance has a very small effect compared to that. Does that make a little more sense?
And the velocity.
Okay, and then velocity, I'm just telling you that's what it is. That has nothing to do with this previous equation. This is just a new equation. The phase velocity equals 1 over the square root of LC. Well, and then I was going to say, and then, yeah, off to the side here, I thought I'd put the equation for mortgage interest over a 30-year period, because just for the heck of it. No, I mean,
What's the relevance?
like what? Who needs relevance? We've got equations. No, so relevance here. The relevance here is we just need to know the phase velocity. So here, this is the limiting cases, and the reason I put this here is because it's only this when the frequency is high. But we're going to assume that the frequency that we're dealing with is always high. Okay? So in general, Z naught is square root of L over C, and phase velocity is 1 over the square root of LC. Okay. And again, that doesn't model dispersion or anything. We're going to kind of ignore that. So, well, no, with
reality, ignoring it.
Well, a lot of this gets that way. Remember I said we're doing this the opposite way? I'm showing you the hard stuff, and then when you see how easy it is when we actually do it, or how slightly less hard it is when we actually do it.
Have we gotten past the hard stuff yet? Or?
That was the hard stuff. Yeah. Okay. Now let's do the slightly less hard version.
Let's water it down. Let's go.
Okay. So now we can figure out characteristic impedance for various devices without having to go through all of this stuff. For a wire pair, the characteristic impedance is 276 over the square root of epsilon log D over A, where D is the distance between the two wire pairs, and A is the radius of each individual wire.
And so the distance would be like the wire themselves. So if you get a certain amount of insulation, that's what's causing the distance.
Right. Yep. The distance is based on the insulation.
Epsilon
And epsilon is just a characteristic of the material in general of copper, and you just have to look it up. Yeah, that would be given to you. Coax is 138 over square root of epsilon log B over A. In general, you'll never use these two equations even, because almost every kind of wire that you use has a set physical relationship here between A and B, and so the characteristic impedances are set already. For example, TV twin lead, we were talking about that earlier, those big flat cables, and then they had the two little spade connectors on the end. and you screwed them onto little things on the back of your TV, they have a characteristic impedance of 300 ohms. And I don't know if you ever saw that on the back of old TVs. It actually usually had it printed on there, 300 ohms, right on the back of the TV.
That's at what distance? Like length of cable?
Length of cable doesn't matter. Yeah, it's just that type of cable. If you had one of those cables that had a big flat connector with two little conductors in the sides of it, and then two little screw-on spade connectors on the end, that's a 300 ohm cable. Because the A and D here were known, somebody figured it out, and it turned out to be 300.
It's not what he's talking about with the overall resistance, like dB loss over length.
Right.
This is about the impedance matching of that cable. Like
Exactly.
Cable's like typically 50 ohm.
No way too far.
Remember the Atari
Well-
600 had a little box where you could switch back and forth between 75 and 300.
That's exactly what
Yep.
It's a little slide.
Yeah?
Did it
What's
connect
that?
cable in the bottom?
Yeah, I have no idea what that is.
You don't know what 2600 is?
Yeah.
Oh my god.
Google.
It's sad days. Yeah, you knew.
Cathode ray TVs.
Well, even those little RF modulators for game boxes. Yeah, and they had two things. One had a little pair of spade bits, and one had a little coax, and then the other side plugged into your game system. Atari 2600 had one, and then you'd flip that little switch, and it said 75 or 300 on there, and 75 would go to the coax, 300 would go to the little spade bits. But yeah, and actually later, I mean, you could get those RF modulators for until fairly. I don't know if you can get them.
Yeah, once the
Yeah.
came out, they pretty much shut that.
But yeah, I remember them for like the Nintendo 64 had one that you could get. It didn't come with it.
Well, I mean, I had something like that, but it was like channel 3, channel 4.
Right, yeah, and then you
Okay.
so
Yeah.
then you put your TV on channel 3 or 4,
Yeah.
and then the old ones used to have, the newer ones just had the coax, and you'd put it on channel 3 or 4. The older ones you could switch back and forth between the coax and the ribbon cable. Those are the really old ones.
Look it up at 2600.
What?
What is that?
Did you?
That I've not seen.
Oh,
Okay.
No, what happens if you
No, I didn't.
don't-
I'm sorry. I never had to.
That's what we're going to talk about. You get reflections, and that's what we're going to spend the rest of the day talking about.
It's got a wood grain, that's tougher along.
Oh yeah, it was fancy, man. You know what just drove me nuts is, man, we saved up, my brothers and I saved up for like months to buy a cartridge for our 2600. And then a couple years ago, my wife gave me this little 2600 that just runs on battery. Well, actually, you could plug it into the wall. It had every 2600 game, and it actually was like hanging at the register at
Yeah, for
well,
like
yeah,
1999.
for 1999. I'm
Yeah.
like, you guys suck, man. We had 3 cartridges, and I mean, it was awesome when we got Adventure. We had saved up for like a year to get that. It was like $50
You buy Pac-Man and have your heart broken because it was such a piece of
because it was such a piece of crap. Yep.
Pitfall.
Yeah, Pitfall was awesome.
Uh,
All right. Anyway,
Okay.
moving on. What's
See,
that?
it doesn't help if we don't squirrel you and you don't squirrel us.
Yeah.
Yeah, I'm not worried about it. So what happens if you don't like pay attention to these characters?
Okay. That was the question here, and yeah, that's the whole point of me bringing this up is we're going to talk about what happens if you don't pay attention. What happens is you get reflected waves, which then take some of your power back and cause interference and do other bad stuff.
There's nothing really with the actual resistance of it.
No, the resistivity of the wire that depends on length has nothing to do with this. This, regardless of length, the characteristic impedance is the same. So for telephone twisted pair, characteristic impedance is 180 ohms. For TV twin lead is 300, TV coax is 75, Ethernet coax is 50. What about Cat5 twisted pair? What's the characteristic impedance? What? 29? Does anybody know?
Still 50?
Nope, it's not 50.
10, 30,
Because that's coax.
10, 9, 8.
More. Okay. I didn't put it on the slide because this is a slide. This is an exercise. Try and find the characteristic impedance of Cat5 cable.
Google it,
Yep.
man. We don't use it.
Yeah, it's 100. Okay.
But that's at 100 megahertz.
Well,
as a fixed.
Right. Well, Captain Sherburne, he found it, man. You were too slow.
Now, is Cat 6 different?
Okay, that's a good question. Is Cat 6? Here you go. Here's your chance. Catch up, man.
No, apparently I don't need to be doing this.
All right, go ahead.
That
Let's
doesn't
do.
say.
Oh, really?
Yeah, go for it.
Frequency that's longer.
Try and
You
find
may now
Cat 6.
regard me.
It's 100 ohms.
With Cat
You
6?
with Cat 6? Oh, yeah.
Yep, that's the same nomination.
I think it's
Ohms. 2002.
So yeah, it does actually.
This
Does
is
years
changed
ago,
since
sir.
then.
10 years.
Yeah,
The cable could have changed, sir.
Yeah, I'm certain that the cable has evolved.
Well, there's like, I know there's Cat 6 and 6 Echo.
You got category 5 and category 6. And it's still 100 ohms.
But but category 6 operates at a higher frequency.
100 plus or minus
Right.
15 ohms.
Yeah, that's what I was
Yeah, okay, and that's what. Yeah, depending on frequency, tolerance is like 15%, which is not great. But and it actually depends on manufacturer too. There are better and worse Cat 6 cables. If you look on Black Box, yeah, they're showing plus and minus 15%. So yeah, Cat 5, Cat 6, both 100 ohms, but close to that, plus or minus 15%. Where are you going to use? Where are you going to care about characteristic impedance mostly? Are you going to care about it for Cat 6 cable? Do you need to match the characteristic impedance at the end of your Cat 6 cables? Is there ever even a way to do that? Well, yeah, there is. But you'd have to build a separate little thing that the Cat 6 cable plugs into that matches the impedance that plugs into your computer.
The
It would be
biggest thing's going
stupid.
to be in wireless transmission systems.
Okay. Anytime you have an antenna, right? Whenever you have an antenna, this becomes really, really important. Cat 6 cable, it is important. It's just as important for Cat 6 cable, but the people that built the NICs knew that it was 100 ohms and built the NICs to match already, right? So yes, it's just as important. You're still going to have all the same issues that you have with antennas and things, except that it's already been taken into account by the manufacturer. It's not that it's not important for that, it's just that somebody already took care of it.
Maybe I'm missing something. So, why are you saying that it affects it? Because of the fact that impedance changes with frequency, or?
Right. Well, because what happens is if we mismatch, if you don't match it up just right, then you're going to bounce like between an antenna and the device that's connected to the other end.
Okay.
And this now it does start to depend on length of the cable. If it's a quarter wavelength or a half wavelength, things are going to be different. We can do little quarter wave matching stubs and all sorts of weird little things that I'll show you today and tomorrow.
Okay.
Yeah, that's what we're coming to right now.
Foreshadowing. Got it.
Right. Okay. So here's what happens. We terminate the line in a load impedance, right? We know that this transmission line has a characteristic impedance of Z0, and so our voltage is V, some rightward going wave and a leftward going wave. What ideally would we want this leftward going wave to be?
Because we want to go
Zero.
Yeah, 0. We don't want to bounce power back and waste it back at the
have interference.
and have interference and all of that. So yeah, we want that to be 0. So this is VR is the incident wave, VL is the reflected wave from the load. Now we can determine how much gets reflected. It's VL over VR, which ends up being ZL minus Z0 over ZL plus Z0 and a phase shift. So in order to make that 0, what should it be? I mean, what should ZL and Z0 be?
The same.
The same, right? If they're the same, the numerator becomes 0 here and we get no reflectivity. So if ZL equals infinity, if we just don't put an end on it, then rho V ends up being infinity minus whatever z naught was over infinity plus z naught, which is infinity over infinity, which is 1. So everything gets reflected. How many of you ever used coax Ethernet? 1? Maybe 2? Okay. Yeah, when you had little T's all the way through there that connected to the different NICs in the machines, but then on the end of that last T, there was a little thing that had to screw on the end of there. I always assumed it was a little cap to keep the bits from spilling out the end, but what else was it probably? Okay, a terminator. Why? Right, because if we have an open circuit, we can see right now 100% of my signal is just bouncing back across along the line. So I'm going to have interference all the way along. If ZL equals 0, if it's a short circuit, then we have minus Z naught over Z naught. So it's minus 1. So we have 100% and a phase shift. If ZL equals 0, 0, then rho V equals 0, which is what we want. Okay, so line impedance is a function of X. So the impedance at a particular spot is given by Z naught times ZL plus JZ naught tangent beta X over Z naught plus JZL tangent beta X. Why do we care what the impedance at a point along the line is? Well, if we're going to match it, we need to know what it is at that point. So if there's a short circuit, if ZL equals 0, then ZX just equals JZ naught tangent beta X. If ZL equals infinity, ZX equals minus JZ naught cotangent beta X. Either way, we're just going to have a pure impedance there. If it's matched, then Z of X equals Z of L equals Z naught. It's the same all the way along the line, and we have no problems.
So how do you compensate for when ZL and Z naught are?
If they're not the same, and you can't make them the same, then you have to compensate by doing what's called a quarter wave matching filter, or there's a thing called a Balun. There's a couple other things, and we'll actually look at those here in just a minute once we figure out how. We need a little bit of stuff to understand that first. Now, measuring reflection, the other way we measure it is using the VSWR, or voltage standing wave ratio. VSWR is Vmax over Vmin, which is V right plus VL over V right minus VL. This is 1 plus the absolute value of the reflectivity over 1 minus the absolute value of the reflectivity. Then transmittivity is how much makes it through if we have a different line spliced to it. How many of you have seen people that did that? I saw lots of people that had like the 75 ohm coax. They twisted off the ground sheath and had the exposed end, and then hooked that to the 300 ohm terminals on an antenna. Saw that all the time. How well is that going to work? Not very, because you have two different wires like this. So we can figure out that V1 equals tau V times VR, where tau V is 1 plus rho V, or in other words 2Z1 over Z1 plus Z naught, where Z1 is the characteristic impedance of this other line. So if we did take a 75 ohm antenna and untwist the leads and hook it to a 35 ohm, or excuse me, a 300 ohm wire, how much voltage would we get through there? Well, we would have 2 times 300 ohms over 300 plus 75
Times VR.
times VR, thank you. Oh, wait.
Because you said tau.
Yeah, tau is that. So times VR, yes, thank you. So we would have 600 over 370, what the crap? It's bigger. Yeah, and actually that's what happens. We would get more voltage, but we would get less current by a lot, and we'd lose power. What happens is, well, let's go back for a second. If we look at that equals 1 plus rho v, right? So rho v is 600 over 375 minus 375 over 375, right? So rho v is going to have, we're going to have a reflected value going back, and that reflected value is going to get added to the rightmost wave. Basically what happens is this. You've got a right wave going in here, then you've got rho v VR bouncing back, but you've also got rho v VR going forward, then you've got the original VR still going forward. So if this is negative, this is going to get reduced, but if it's positive, you're going to get more voltage going forward.
So we're out of hard stuff right now.
This is the easy stuff. No, this is the, I said, the slightly less hard stuff. Slightly less in that you're given an equation, all you're going to have to do is plug stuff into the equation. It's a annoying equation maybe, but okay. So a couple ways to measure reflections. First way is rho v. Here's rho v versus VisWAR versus tau v. You notice that rho v and tau v, rho v is going to be 1 plus tau v. So minus 0.82 plus 1 gives us tau v, gives us 0.18. So if z1 over z0 equals 0.1, then you get 0.82 and 0.18. This goes up to 1 at 1 and then starts going back down. We're not going to worry too much about it. Now the fun part. Everybody loves Smith charts. Exactly. Did anybody see that old Disney movie, The Black Hole, way back in the day? That's where this, I think Smith invented this from looking at that. No, actually, if you look at this, this is just, okay, think of this as being, the top of this is the straight up and down y-axis, and the bottom of this is a straight up and down the y-axis going down. So we took a regular graph and we curled it over there. So this is the x-axis, that's the positive y, that's the negative y, and it goes to infinity over there. So all we did is we took a regular graph, curved the y-axis over so that it touched over here at the other side.
Like the gravity well.
Yeah, like the gravity well thing. Exactly.
So just like non-Euclidean geometry?
No, now this is just a way to figure out, okay, we have equations for, and the things you're going to want to find out are rho v, VisWAR, and z at a point along the line. Smith chart is just a way to do that, either to sanity check yourself, so that make sure your equations are right. What's that? Or make you insane. Yeah. Let's take a break. We'll come back and I'll